Okay, today's lesson deals with the difference of squares. So in order to use this special factoring pattern, a couple of things have to exist and be in place. And if any of these things fail, you cannot use this factoring pattern. First of all, you should be definitely familiar with your perfect squares, so make sure you know your perfect squares. All right, in order to determine whether you can factor using the factoring formula of difference of squares, first of all, you want to look to see, do you have a two-term polynomial, otherwise known as a binomial? Two terms, check. Next, we want to look to make sure each one of those binomials is a perfect square. 4 definitely is a perfect square. X squared, well, hopefully by the square right here, indicates that it's a perfect square. So check. And the last thing we need to check on is we need to see whether or not we are subtracting those two terms. Check. If all those three things are in place, you can factor using the difference of squares formula. And that formula is just a matter of you taking the square root of each individual term. The square root of x squared is x. Square root of 4 is 2. And then you put a plus and a minus. These things, I think we've discussed this term, are referred to as conjugates. And this pattern will always work. Well, let's just say for an imaginary moment here that you really didn't understand this pattern. We can actually turn this into a three-term polynomial. You could look at this as x squared plus 0x minus 4, because if you notice, your x term happens to be missing. And if that's the case, well, then we can look for factors of -4 that add up to give me 0. And the only pair of numbers that you can multiply to get a -4 that add up to give you a 0 would be a +2 and a -2. And hence it would still factor to the exact same pattern. Would have been nice if I actually recorded that last one. Oh well, I'll just record a couple more. All right, the third example, we have a to the 4th minus 9b squared. So now we've got more variables to deal with than anything else. So the question you've got to be asking yourself is, how do I determine whether or not a variable with an exponent is a perfect square? So I'm going to go off to the side here, and I'm going to do a couple of things. So imagine I took x to the 3rd. If I squared it, remember our rules to exponents, when you have a power raised to another power, you multiply the exponents. That gives me x to the 6th. So x to the 6th is a perfect square. I'm going to do that with a couple of values. Let's try x to the 5th. If I square it, anytime you square anything, you get a perfect square. That's x to the 10th. Well, how about x to the 8th? Square that. That gets me x to the 16th. And I could keep going on and on and on with this. I already picked 3, so let's pick a different value. Erase that. And let's do 7 squared x to the 14th. What do you notice about all of the exponents in all of these perfect squares? Hopefully you recognize that they're all even. If you have an even exponent, then your variable is considered to be a perfect square. If to get a perfect square you have to multiply something by 2, when you take the square root of it, then you're just going to divide the exponent by 2. So now going back to example 3, we've got our two terms, check. Hey, that's an even exponent, that's an even exponent, and 9 is a perfect square, so both are perfect squares. And then, yep, we're subtracting the 2, check. So now I can write my parentheses, and I have to take the square root of each of those. So again, to do a square root of a number with a letter with a variable, let me speak this right, a variable with an exponent, all you have to do is take the exponent and divide by 2. That is its square root. So a squared. Square root of 9b squared is 3. Half of 2 is 1. Again, you don't need to write the 1. 3b, 1 plus, 1 minus, and that is your final answer. Okay, so these are a couple of examples from the ones on the back that were yours to try. So I'm going to do that very first one. Whoa, didn't mean to come back to that. Erase that. And this was the 36 minus x squared. Again, checklist, two terms, yep. 36 a perfect square, yep. X squared a perfect square, yep. And then is there a minus between the two? Yep. So you're good to go. Factoring pattern. Because the 36 comes first, the square root of 36 has to go first in your answer. The order is important. If you flip the order of this, the answer is not the same. Square root of x squared is just x. And again, 1 plus, 1 minus. And you're done. All right, I'm jumping to number 4 from your practice problems. 81x squared plus 36. All right, going through our checklist, two terms, yep. Perfect square, check. Difference between the two, fail. That means this problem cannot be factored using the difference of squares factoring formula. However, that doesn't mean that we can't do something with it. Anytime you're given a problem, you should always look for a GCF. So even though it doesn't fit our factoring pattern we were just working on, that doesn't mean we can't take something out of this. So there is a number that divides evenly into both 81 and 36, and that happens to be 9. So we can divide that out. That leaves with 9x plus, or 9x squared, pardon me, plus 4. And again, you might look at this and go, hey, aren't this a difference of two perfect squares? Close, 9x squared is a perfect square, and 4 is a perfect square, but notice that stinking plus sign is still there. So therefore, this answer right here is as good as it's going to get.